experiment 8, coordination complexes of cobalt-3. For the purpose of this experiment is to prepare a series of cobalt complexes. So we learned the complex ions in class, right? So here we'll study the cobalt, ammonia 5, and L. So this L can be ammonia, chloride, water, NO2, and NO. And the Z here is the charge on the complex ion. So for example, if the L equal to ammonia, because there's no charge at ammonia, and the Z here will equal to the same charge as cobalt will be 3. And if the L equal to Cl minus, because there's a minus charge there, 1 minus charge there, then the Z here will be cobalt 3, that's a 3 minus 1 equal to 2. So the complex ion will be 2 plus 1L equal to Cl minus. And this is one example of the when the L equal to Cl. So that's one of the complex compounds. So how are these compounds made? The detailed procedure of making these compounds are in the experiment procedure on Canvas. Basically, these all different complexes are initially prepared from cobalt ammonia 6 3+ ion, which is formed in the presence of a cobalt-2 chloride with ammonia and hydrogen peroxide. So in the cobalt-2 chloride, we use hydrogen peroxide to oxidize the cobalt-2 to cobalt-3. And with the excess amount of ammonia, that forms the cobalt-3 ammonia 6 complex. Okay, when that complex is formed, we add other ligands, Cl or water or NO2 or O, and that can form other complex ions. Again, the detail of that you can find on the experiment procedure on Canvas. So we will use the visible data of the cobalt-3 complex to understand its crystal field diagram. So we're going to collect all the visible data, all the visible spectrum from all 5 cobalt-3 compounds. So this is a little background of the crystal field diagram, which you probably learned from the lecture. So for cobalt-3, which is this 6 metal, it has 6 electrons in the d orbital. When there is no ligand present, the 6 electron will be having 1 pair in the ground state and 2 singlet and in the ground state as well, and the 2 singlets and on the excited state as well. So that's a paramagnetic. When there is a ligand present, the delta zero, the energy difference between these 2 states is larger than when there is no ligands. So all the electrons goes down to the ground state and paired up. That becomes a diamagnetic. The difference in the energy in the crystal field is called the splitting energy delta zero. The delta zero is dependent on ligands. And the one we use in different ligands, we can see the delta zero can be a little different. This energy is responsible for the different color of compounds. You can imagine when the light mixed with all wavelengths is shining on this compound, only certain energy that fits this gap can be absorbed to excite the electron to the higher energy orbitals. If we have the absorbance versus wavelengths data from the compound, we can look at the maximum absorption peak. That wavelength has to fit into the energy difference here. Okay, then based on the absorption maximum, then we can calculate the energy difference. So here I show you this visible spectrum that we use in last experiment. So the vertical axis here is the absorbance. The horizontal axis here is wavelength. For 5 different compounds, we can see the maximum absorbance wavelength is different, right? For this one, the lambda max is around the 540. For this one, you can see move to 500, and this one moved to about 480. So everyone is different. That's also why they look different color when they are in solution. So we can measure their visible spectrum and look at the lambda max, and we can calculate the splitting energy by the lambda x. We use the LabQuest unit together with the SpectralVis. The detail of the mechanism of the spectrometer can be found in the experimental procedure. Okay, and remember, every time when you start to take a measurement, you need to calibrate the instrument by running a blank first. So once you finish your measurement, the spectrum will be saved in the LabQuest, and you can export the data in an Excel spreadsheet. So we'll provide that data in Canvas. So on Canvas, you'll find the Excel spreadsheet. Once you have that data, you need to plot it using absorbance as a vertical axis and wavelengths as the horizontal axis. And then you need to identify the lambda max. So lambda max is the wavelength at which the maximum absorbance occurs, or the peak position of the wavelength. So once you have the lambda max, you can use this equation from the theory of relativity, E equal to h times nu. Nu is the frequency of light, which equal to the speed of light divided by the wavelength of light. So the lambda here, the wavelength of light, is your lambda max, okay? And the speed of light is a constant. The h here is a constant, it's a Planck constant. So 2 constant, and you have the lambda max, and then you should be able to calculate the splitting energy delta zero. So we need to calculate all energy difference for all 5 different compounds. We can determine the relative impacts of ligands. So you can see different ligands will result in different delta zero, which is the different crystal field energy, okay? And we need to put all 5 different ligands into a series based on their delta zero, the ligand strength. And this is referred to as the spectrochemical series of ligands. So basically just arrange different ligands according to their delta zero, the energy from large to small, then that is our spectrochemical series of ligands. And in the lab report template, you'll find the table 1 here. You need to use the information you get from the spectrum and the calculated result to fill in this table 1. So you need to fill in what the complex is and what color they are, and the concentration, and this concentration is provided to you. Identify the lambda max and calculate leave delta 0, and fill in the table 1. And the last column is the epsilon. So based on Beer's law, the absorbance equal to epsilon times L times C. The L is the light path, which is the thickness of our cuvette, that is 1 centimeter, and the C is the concentration, which will be given in the laboratory template. So you will use this Beer's law equation. You have L, you have C, and you have the absorbance at the lambda max. When you know A, L, and C, you can calculate epsilon. So I want you guys to calculate the epsilon and the fill to this column here, okay? And make sure your table lists the complex in order of decreasing delta 0, decreasing splitting energy. So on Canvas, there is an experimental procedure, and there's also laboratory template. Make sure do your calculation and fill out the data table 1. And there is also visible data for compound 1 through 5 that you use that to plot the visible spectrum in Excel. Okay, so what you need to do, download the lab report template and fill out to the data table 1, download the visible data, and plot the absorbance versus wavelength for all 5 compounds, and include that in the lab report. And there are also a bunch of questions there. Please answer those questions.